So far, we've taken a look at the structure of the nucleus. And at that time, I pointed out that not every nucleus is stable. As a general rule of thumb, every nucleus wants to eventually become iron if it could, because that's the most stable nucleus with the highest binding energy per nucleon. Now, plenty of nuclei are stable enough and won't decay. But there are plenty of others that will. So let's go and take a look at how that happens. And it turns out that there are three major types of radiation, which are ways that nuclei can try to get closer to the ideal of being iron. So they get the names alpha, beta, and gamma because back in the day when radioactivity was first being explored by people like the Curies, they knew that they were looking at three different kinds of radiation, but they didn't know what they were. So they picked the first three letters of the Greek alphabet. We now know what these types of radiation are. So alpha is a helium-4 nucleus. So remember, in our usual way of writing this, we put the atomic number here, mass number here, and the chemical symbol here. So this is a bound state of 2 protons and 2 neutrons. Beta decay turns out it can be either beta plus or beta minus. These are charged particles. Beta plus corresponds to a particle called a positron, and beta minus to an electron. Now, a positron is not the same thing as a proton. It does have the same charge as a proton, but it has the same mass as an electron. Actually, it's the exact same kind of particle as an electron, except for the fact that it is positively charged. The positron is what we call the antimatter dual to the electron. Then finally, gamma radiation are high energy photons. So probably be easiest to go ahead and work in these with these in kind of reverse order. So let's go ahead and take a look first at gamma radiation. Now, we encountered this already when in the unit on relativity, we were looking at the proton-proton chain that was occurring in the sun. And at that time, we said that one of the steps in the proton-proton chain was that a helium nucleus would get together with a hydrogen nucleus would get together with a hydrogen 2 nucleus, which is, or also known as deuterium. It's the isotope of hydrogen with 1 proton and 1 neutron. And what we would get was a helium-3 nucleus, but it was in a nuclear excited state. So if we go back to thinking about the shell model here, I can have my neutron shell and my proton shell like so. I've only got 1 neutron sitting in the neutron shell because this is 2 protons, and since the mass number is 3, that's be 2 protons plus 1 neutron. So originally what's happening is I've got a proton in an excited state, and then that proton in the excited state will transition its way down to the ground state, like so, emitting a photon in the process. So then if we look at our energy level diagrams afterwards, here's my neutron, there's my proton, I end up with that as the final state after the photon took out the energy from the nuclear excited state. So then we usually just write these excited states as star. So then we just note the ground state without the star. Okay. Probably the next useful one to look at will be beta decay. So beta decay is where we emit either a positron or an electron. So, for instance, let's go take a look at the decay of carbon-14. So carbon-14 has 6 protons and a mass number 14. So it's 6 protons plus 8 neutrons. So what's going to happen is it's going to become nitrogen-14. And the way that's going to happen is one of the neutrons is going to become a proton via the weak nuclear force. So a way to kind of keep this straight is to do what I call nuclear stoichiometry. And so for our beta particle, which, since that's an electron, I mentioned this in the previous video, we can give an electron a pretend atomic number of -1. Now, it makes no sense to give an atomic number to an electron, but you use this for balancing things. And you give it a pretend mass number of 0. And so just like you do stoichiometry in chemistry, what you do is you just make sure that both the top and the bottom lines balance here. So 14, what do I add to 0 to get 14? Well, the product has to have a mass number of 14. What do I add to -1 to get 6? Well, that'll have to be 7. 7 is nitrogen. Now, this isn't quite right. It turns out there's one more particle that gets made. So this is our electron, and since to balance what's called lepton number, the weak nuclear force requires that an object called an electron antineutrino get made. This thing has 0 charge and almost no mass. We do know definitively that its mass has to be greater than 0, but all our best measurements can basically say it's greater than 0, but it isn't much greater than 0. So this is important when you're considering things like the signature of exploding supernovae or something like that. But it turns out that this particle, which I'm even just drawing in gray so we don't make a big deal about it, for the most part, it pretty much doesn't interact with us at all. To attenuate a beam of neutrinos by 1%, you'd have to shoot them through a light year of lead. So you can have no end of neutrinos flying right through you, and literally neither you wouldn't notice the neutrinos and the neutrinos wouldn't notice you. But to be official, that is part of the bookkeeping of the process. So you can also have the process go the other way. You can have particles emit a beta plus and turn one of the protons in the nucleus into a neutron. If you do that, then when you're bookkeeping the neutrinos, that would be just a regular neutrino rather than antineutrino. Okay. So then finally, let's go and take a look at alpha decay. So now alpha decay, what's happening here is, especially in more massive nuclei, an alpha particle being 2 protons and 2 neutrons, you can fill the lowest proton shell and the lowest neutron shell completely. And so it actually makes for a pretty darn stable little particle. And so when you have an unstable nucleus, often it's not bad to model it, and this is more of a mathematical approximation, but it isn't bad. So this is our larger nucleus. And we can model it as having an alpha particle, a helium-4 nucleus, rattling back and forth inside. Now, the strong nuclear force from all the other protons and neutrons will endeavor to keep the alpha particle constrained. However, it is possible for the alpha particle to escape. So in this video that you're looking at right here, what you're seeing is the wave function for the alpha particle as a function of time. The big blue lines on the sides correspond to the walls, if you will, of the nucleus. And theoretically, you would need so much energy that you shouldn't ever be able to get out. But if you remember earlier in our treatment of quantum mechanics, quantum mechanics allows, the wave treatment allows for particles to tunnel through potential barriers that they classically shouldn't be able to with some probability. And so what you're seeing here in this is a computer simulation showing where the particles are ending up. And you can see that with time, the probability that the particles will end up outside the nucleus keeps getting greater. So, when that sort of thing happens, let's take a look at, say, uranium-235 as an example. Now, if I go take a look at uranium-235, that is something that likes to emit an alpha particle. So again, we can do the same kind of double stoichiometry thing. So uranium-235, atomic number 2, mass number 235, chemical symbol U. And again here, well, an alpha particle is a helium-4 nucleus. So again, we can do stoichiometry on both the upper and the lower numbers. So what do I add to 2 to get 92? 90. And what do I add to 4 to get 235? That would be 231. If I go look up 90 in the periodic table, that's thorium. So one of the modes by which uranium-235 likes to decay is to emit an alpha particle and leave behind thorium nucleus. Now, in these radioactive decays, the nucleus you start with is called the parent nucleus, and the one you leave behind gets called the daughter nucleus. I have no clue why it isn't parent and child. All the literature calls it parent and daughter. That's just how that seems to work. All right, so here you're looking at what we call a radioactive decay series for uranium-238, a different isotope of uranium than what we were just looking at. So here it follows the same kind of process. Uranium-238 can get to the daughter nuclei can have a lower binding energy per nucleon if it emits an alpha particle. So that would decrease the atomic number by 2. So we go from 92 to 90. So uranium becomes thorium. And we would decrease the mass number by 4. So 238 goes to 234. Now, it turns out that at this point here, there's actually a few too many neutrons for stability. And so a way that things can become more stable is if some of the neutrons become protons. And they'll do that by beta decay. So with beta decay, the mass number doesn't change. But if we emit a beta minus, then in order to conserve charge, the number of protons had to go up by 1. So we'll emit 1 electron here and go from atomic number 90 to 91. Then from 91 to 92, but now we are at U-234, which is also not stable. Its preferred decay, one of its preferred decay channels is to emit another alpha particle. So we're back to thorium, but now it's thorium-230. So here we can drop from thorium-90 to radium-88. Again, dropping the atomic number down by 2. Radium-226. We drop the atomic number by 2. We drop the mass number by 4. Then to radon-222, which is a gas. Atomic number 86, mass 22. And then to lead-214. And then you'll have a couple of more beta decays working your way up to bismuth-214 and polonium-214. Another alpha decay to lead-210, then bismuth-210, polonium-210 by beta decay. Then another alpha decay to lead-206, which is stable. So this is a very long-lived parent of the decay series, and this is the stable daughter end point here. Now, I didn't draw in all of the possible paths there. Some of these have a bit of a choose-your-own-adventure kind of flavor to it, where alternately you could go through some other beta decays and alpha decays, but this is one of the main paths down. Now, it turns out that you can use this to do things like date rocks. So how does that work? Well, so to that end, we need to start talking about radio half-lives. Oops. So the thing is that any of these decay processes are random. And so the way I kind of like to think about it is, one of my favorite sayings about playing the lotto is that someone will win it and it won't be you. Now, why can I feel so confident about both of those statements? Well, it's just plain because the odds of actually winning the lotto are, depending on the exact game you're playing, are something on the order of 1 in 300 million. You are more likely to get killed by lightning this year than you are to hit the lotto, and I mean by a lot. So, so if you're planning on hitting the lotto, you should really be thinking about taking out lightning strike insurance. But I can also be very confident that someone will hit it, because over the course of a few draws, they'll have pretty much sold, at least 300 million bet slips. So somebody will have ended up holding the bet slip. Okay, now let's change up the game a little bit. Let's say we imagine that we have a sample of radioactive material here. So I'm just drawing a whole bunch of nuclei here, like so. And each one of these has a chance of decaying. So we can imagine that after some amount of time has passed, it's effectively like we had a drawing. And maybe early on, several of these hit all in pretty short order. Well, now what will happen is that we have fewer bet slips effectively in play. We've got fewer nuclei left that could decay. So that's like playing fewer bet slips. So that means that we wait the same amount of time, we'll have fewer decay, and so forth. So what the deal is it turns out that the rate of decay is proportional to the number of undecayed nuclei. Now, we've run across this before, believe it or not. If you think back to when we were looking at RC decay in electric circuits, the rate at which a capacitor discharged was proportional to the amount of charge it held. And at that time, we saw that the amount of charge held would go as some sort of decaying exponential. It's the exact same logic process here. So if n is the number of particles I still have left, it'll be whatever I started with, n naught times e to the minus t over tau, where tau is our decay constant. Now, it turns out that in the field of radioactivity, we tend not to work in, professionals tend not to work in decay constants. They instead work in something called half-lives. The symbol is very cleverly T1/2. And if you play around with doing the algebra, you can get that'll be this decay constant times the natural log of 2. So this is approximately 0.693 times that decay constant. The reason that's convenient is we can then write our number of remaining particles as our number of original particles times 1/2 raised to t over the half-life. So the way we can interpret this kind of thing, so say if I plot, there we go. So this is my number of particles. This is time. So let's say this is my initial number and naught. So we have 1 half-life, 2 half-lives, 3 half-lives. So at time 0, I'll start with n naught of them. And then just very simply, after 1 half-life, I'll have literally half of them left. And then after 2 half-lives, what I'll have is 1/4 of them. And then after 3 half-lives, I'll have 1/8 of them. So it'll decay. It's an exponential decay like we've seen before. And when we characterize it by half-lives, basically we're saying after 1 half-life, I have 1/2 of it left. After 2 half-lives, I have 1/2 of 1/2 of it left, or 1/4. After 3 half-lives, I have 1/2 of 1/2 of 1/2 of it left, or 1/8, and so forth. Now, since the rate of decay is proportional to the number of particles I have, I can just in fact, it's actually going to be, we can define it as the number of particles I currently have over the decay constant. So again, putting in for half-life, so we'd write this 0.693 times the number of particles I have over the half-life. And following that same logic, we can say that our the current decay rate will be e to the minus the initial rate times e to the minus t over tau, or more commonly, we would write it as the initial decay rate times 1/2 raised to the t over the half-life. So for instance, if you buy some sort of radioactive source, say for medical use or something like that, it will have the activity level and the manufacture date and the activity level on it. Now, if you wait 1 half-life after the manufacture date, the activity level will be half of what's stamped on it. After two half-lives, it'll be 1/4, and so forth. Okay. All right, so let's do one example of how we can use radioactivity to date something. And the example I would have here would be carbon-12 dating. Now, the way this sort of thing works is that in the atmosphere, there are constantly very high energy particles coming in from outer space called cosmic rays. Why they get called a ray is a historic thing, but they're really highly energetic particles. Now what happens, there'll be just some random nucleus sitting here. Nucleus. And these particles come in from outer space. They're actually the remnants of very energetic astronomical events. Will blow these things apart. And what's important to us here is that some of the things that come flying out of this are neutrons. So, the atmosphere is mostly nitrogen, and the stable isotope of nitrogen, one of the stable isotopes of nitrogen, the most common one is nitrogen-14. And we can have a neutron come and hit it. Now, what winds up happening is the neutron boots out a proton and ends, but the neutron itself gets absorbed into what was the nitrogen. So let's figure out the daughter nucleus. So what do I add to 1 to get 7? That would be 6. What do I add to 1 to get 1 plus 14? Well, 14. So carbon-14. Now, these cosmic rays have been coming in at pretty much a constant rate for a very long time. And so what this means is that in the atmosphere, there's a pretty reliable ratio of carbon-14 to the more common isotope carbon-12. Then the carbon-12 will itself undergo beta decay. Carbon-14 dating, what am I saying here? So the carbon-14 will undergo beta decay. To be turned back into nitrogen-14. So we go ahead and eject an electron. So do I add a -1 to get 6, I get 7. What do I add to 0? I get 14. So I get nitrogen 14. And again, there's an electron antineutrino. So that's the beta decay process. And it turns out that the half-life for this process is 5,730 years. And so you can use this actually to date the remains of organic material. Like, let's say you stumble across in an archaeological dig the remnants of a campfire. The trees would have been bringing in carbon dioxide from the atmosphere. And because of this process that was occurring in the in the Earth's atmosphere from the cosmic rays, the ratio of carbon-14 to carbon-12 in the atmosphere is a known number. So if you then go and take a look at the rate of beta decay happening in the sample after the tree's been cut down and burned, doesn't have any mechanism by which it can replenish the carbon-14 it has. So that carbon-14 starts decaying. So as an example, let's say that the rate that you measure from the sample would be 10% of the rate you would expect from a live tree. We can then ask, how long ago was that campfire burned? So we can go ahead and say that the current rate is the initial rate times the half-life times 1/2 raised to t over the half-life. Okay. Rearranging, this is 1/2 t to the t t1/2 t over t1/2 equals r over r naught. And I can take the natural log of both sides. Doing that will give me t over t1/2 times the natural log of 1/2 is equal to the natural log of my current rate over what the initial rate should have been. So rearranging some more, I get that the time elapsed would be the half-life times the natural log of r over r naught over the natural log of 1/2. So the half-life of carbon-14 is 5,730 years. So we times the natural log of, we said we decayed down to 10% of our initial rate over the natural log of 1/2. Now, it's useful to estimate, r naught over r naught, and the r naughts will cancel. It's useful to estimate these things. So this natural log, so this 0.13. So remember, every half-life you drop by 1/2, right? So 1 half-life would be 1/2, 2 half-lives would be 1/4, 3 half-lives would be 1/8, which would be 0.125. So we're expecting the answer to be a little more than 3 half-lives. And so we're expecting an answer on the order of something bigger than 18,000 years. And sure enough, it turns out that when you crank this through, it's 22,400 years. Let's get into some of the biological effects of ionizing radiation. Any of these particles, it doesn't matter what it is, alpha, beta, or gamma, can go flying in to some nucleus that's probably, or fly into some atom that's part of some complicated, probably some potentially complicated molecule, such as DNA. So here we would have our electron in orbit. The collision will basically cause this thing to shoot through more or less undeflected, so slightly low. And it'll give up some energy, but it won't give up much because these things are pretty energetic to begin with. Slightly lower energy. And what you end up with is an electron that gets ejected. Importantly, what this will also do is it'll start to break chemical bonds. So for instance, if this is a DNA molecule, you've now damaged the DNA molecule, and you could potentially cause mutations, and those mutations in turn could cause things like cancer and stuff like that. Now, a general rule of thumb is the heavier the particle, the more damage it does. So alpha particles do the biggest damage. It'll be more damage. But the shorter the distance it penetrates. That's because this is basically, if this is an alpha particle, it's basically blowing through molecules like a Mack truck, plowing into all of them, does a lot of damage in a small area. Lighter ones go the other way around. Less damage. Lighter things tend not to give up as much kinetic energy in a collision, but as a result, they can penetrate for longer distances. That's why for the most part, with the exception of radon, we tend not to get too stressed out about alpha emitters. Unless you've got open cuts on your hands or something like that. You got plenty of dead skin cells in your body, and they actually do a pretty decent job of blocking a lot of that radiation. On the other hand, radon is an alpha emitter. We saw that in the Decay series. And since it's a gas, though, that means you can breathe it in. And that means it can come into direct contact with live tissue in your lungs. And so then this is more serious because damage to dead skin cells, didn't matter so much. You're going to slough that off anyway. Damage to live lung tissue, now you're talking about a risk of lung cancer. So this is why a lot of homes have to have radon mitigation systems put in. And this is because of trace radioactive elements that were in the aggregate that made up the foundation. As they decay, they wind up emitting radon gas, and then you can end up breathing it in. And radon being heavier than air, it has this tendency to just accumulate in basements of houses. With time, though, it can become an issue. But with a mitigation system, what you just do is you literally just keep pumping air off the bottom of the basement where the radon's going to be hanging out, and you vent it out. And at that point, it will dilute enough that it won't be a problem. All right. So to characterize the amount of damage that we can do, the way that the SI units for radioactivity, and there are a bunch of units out there, but I'll give the SI ones. So radioactive doses. Active doses. So the usual unit for characterizing dose is the gray. And that is defined as delivering 1 joule of radiation per 1 kilogram of body tissue. So as mentioned, not all radiation is created equal. If you're trying to characterize the damage being done, there's what's called the dose equivalent. And so the unit for that is the sievert. And it's the radiological biological effectiveness factor. Yeah, that's a mouthful. Times the dose, which should be in gray. So this is characterizing how much damage you could do to the tissue. So this is a number you can find in tables. And for instance here, an X-ray would have a value of around 1, but an alpha particle would have a RBE of about 20. So in other words, to our hypothetical lung tissue, for the same number of joules per kilogram of dose, alpha particles do about 20 times more damage than X-rays would. Now, these are rough numbers. More sophisticated tables will take a look at both the type of radiation and the tissue being affected. Now, an older unit that you may run across, because it still shows up in a lot of medical literature, is the REM. And that's 0.01 sieverts. This stands for Rankton equivalent man. Yeah, sievert is probably the more common unit to use now. So to give some example for how that might work, let's say that you want to compare the how much comparative damage you could do giving somebody a whole body CT. Which that's X-rays versus a chest X-ray. So over chest X-ray. So a typical value for whole body CT is going to be something like 12 millisieverts to the whole body. Let's model our person as 75 kilograms. On the other hand, a chest X-ray is going to be something like 0.2 millisieverts, and that'll be just to the tissues in the chest, about 5 kilograms. So let's see how many chest X-rays a whole body CT would amount to. Well, first off, since this is X-rays, the RBE is equal to 1. So that means in this case our doses will also be the same number but in grays. So our doses will be 12 milli gray and 0.20 milli gray. All right, and that will work out to be 0.012, and a gray is a joule per kilogram. And this will be 0.0002, and again, a gray is a joule per kilogram. So when we take our dose, like so, this will be 0.012 joules per kilogram times 75 kilograms, because that's delivered to the whole body, versus the chest X-ray, 0.0002 joules per kilogram. times 5 kilograms of tissue affected. This turns out to be a ratio of 900. So giving a patient a whole body CT will give them a total dose that's like the equivalent of putting them through 900 chest x-rays just across their whole body. So this is the sort of decision that doctors have to make when figuring out whether to order images of their patients or not. Is they have to weigh the fact that when they order an image, they are going to be exposing the patient to radiation, and they have to decide that the risk of what the radiation could cause is worth the diagnostic information to treat whatever the more pressing concern is. Now, sometimes you want to do this sort of thing intentionally. So a good application here would be crossed beam radiation therapy. So let's say you've got a tumor sitting in some tissue. Now the trick is you would like to get rid of the tumor, but without affecting the surrounding tissue. And one of the games that you can play is you can expose a patient to radiation in these pencil shapes. So a fairly low dose in that pencil, for instance. And then another pencil of radiation angled a different way that also happens to include the tumor. You would expose all of this tissue to, again, a fairly low dose, which hopefully won't be causing any problems. And then maybe you angle it still yet some other way. And the idea is that if you are sufficiently clever in designing where all the pencils of radiation go, the cumulative dose at the tumor will be enough to kill the tumor. So we'll have a high dose at the intersection. But hopefully low enough doses everywhere else that it won't create more problems than it would solve. All right. So I think that we'll go ahead and do it here. So if you've stuck through this whole video series, I thank you very much, and I hope to catch you again at some other point.